Okay, so we've talked about the models, the primary ways that information seem to move from the outside world into the internal representations that we have. Today, I want to talk about some of the core uh, factors or features that lead to optimal learning conditions for the typical learner. The key to today's presentation is that regardless of what model of learning you tend to adhere to or believe in or trust the most, these are the principles of learning that we've demonstrated work most effectively across the most settings and tend to provide the underlying mechanisms or strategies that people have the greatest probability of retaining information long term. So here we go. First of all, I want to start off with a quick definition of what I mean by forgetting. I'll say this over and over again throughout this class that I prefer to explain forgetting as a failure to retrieve. That means the information is not gone or can't be obtained in a different time frame. But forgetting is simply that I, at this moment, don't have access to that information. There are two primary explanations of forgetting that have existed over the course of the development of information processing models. The first one is interference. This is the dominant theory today in most contemporary models, suggesting that there's something going on that's blocking your ability to retrieve the content. That can be interference that comes in working memory. That can be interference that comes in during the retrieval from long-term memory. That can be interference at the time of encoding. Also, decay is another model that is out there, another explanation that's out there. Most serious cognitive psychologists will point to problems with the decay theory because the issue that arises is you can't really pinpoint any specific memorial or mnemonic process that is decay. Basically, decay is a time-based uh, loss of information, and it's really hard to pin down because it doesn't happen in a standard format. The longer you allow something to go without rehearsal or retrieval or activation, the more likely it is to get interference. So how much is decay, how much is interference? And then there are other things that just stay, whether or not you rehearse them. So decay is not a very strong universal explanation for learning or for loss of learning or loss of information or failure to retrieve. So it tends to be tenuous and one of those things that leads to more arguments than explains anything. Now, the reason it hangs on so well is phenomenologically, it makes sense. You have this notion, this feeling that it's just like degrading and falling apart. But as I talked about in the other video, that doesn't really work out quite like that. So to give you an advanced organizer, in your book, they talked about advanced organizers as an effective strategy to help people organize their content. So I thought I'd show you one. This is an advanced organizer for today's presentation. These are the topics I'm going to cover. There's a lot, so you may need, pack a lunch for this one, or pause it and break it up. And you can see because they're separate sections, there's lots of opportunities to segment and break up your learning. We'll talk a little bit about that when we talk about cognitive load theory at the end. If you find yourself just like plowing through and just get it done, that kind of thing, stop, segment your material. There's a pause button. Just use that, and then take notes and move on when you're ready. There will be no penalties or failures or inabilities in your memory if you pause the video. It's built that way. Okay. First of all is attention. First thing we're going to talk about. It's a critical feature in all memory models, and it is necessary in order for you to have any possibility of having a long-term memory outcome or a short-term memory outcome. A couple of things I like to just point out. I'm not going to define everything on these videos. I just want to call your attention to them as you're going through. First of all, you have both selective and sustained attention. Selective attention means I'm picking out the elements of the learning environment or the materials that face me that are relevant. If you're paying attention to that warning sign on the slide, then you are not using good selective attention, even though I baited you with it. So that's bad design. But that's not the important stuff on this slide. So stop paying attention to that. Use good selective attention and pay attention either to what I'm talking about or to the content on the side that is going to help you move forward. I'm going to bring up something real quick. I'm going to use my laser pointer so that I can help increase your attention. So signaling is an attention getting process that instructors use, that books use. You know, they highlight, they bold, they do some sort of arrow pointing, sometimes just to get your attention on the thing that needs to be. The signaling principle is a very strong process that you know, is common sense, but research also supports it, which is the best kind of common sense. If I draw your attention to that content, it increases the probability that it'll get through that attention gate we talked about before, and increases your probability of being perceived and held in working memory. Now, another aspect to attention is, as an instructor or an instructional designer or somebody who's building a learning resource for somebody, you also want to reduce your distracting information. There's a lot of research that was done on something called the seductive detail effect, and that was an effect that demonstrated that learners, when they read interesting, embellished stories in textbooks, often remembered the interesting pieces of information, the interesting facts, the one-off, funny, quirky things. So you might remember this sign from this lecture, but you may not remember the content of the lecture. These seductive details, one of the presumptions was that it's drawing your attention away from the core content. For instance, one of the classic studies was you know, a textbook passage that was built to talk about what lightning is and how lightning works, and you know, the kind of the atmospheric science around lightning. And one of the things the people who read the book chapter or the textbook passage remembered most often is how many people are struck by lightning a year. Well, it's not at all interesting to the scientist, basic information, or it's not central to their core knowledge. So that information drew the attention of the individual away. It was the presumption of that work, and made the core information less likely to be retrieved. Other things that you can do to increase attention is to vary your presentation. That could be within one presentation or across multiple presentations. Don't do the same thing all the time. I had a high school Algebra 2 teacher who was great, by the way, but she sat down. We knew every day what was going to happen. She was going to sit down. She was going to pull out her overhead projector marker, and she was going to do problems. And we were going to do the problems right along with her. Sit on her little stool with her little black marker. It was always black, no different colors, and just go to work on that overhead projector. Variations in your instructional style will draw more attention. You can change your pace. You can change the modality. So if you speed things up and then slow it way down, when you're working with people with varied abilities, that's critical. But with anybody, it also works. You'll also notice that if you bring your voice down, it'll draw attention in sometimes. And if you get real excited sometimes and then bring it down real low, that will also change the level of attention that someone is paying. I'm not talking just about in instructional settings. This will help any instructor, but I'm talking about in any format where I'm trying to grab someone's attention. So if you're talking about marketing, you know, some sort of commercial, you know, building a commercial or trying to draw someone's attention to content, you can use all these sorts of things. If you see a really good public speaker, they do this very, very well. They know you can't just go full speed with a crowd in order to keep their attention. You have to draw it down, let everybody get their breath, and then you build it back up again. And then finally, if you really want to get someone's attention on something, you engage them in it. You make them do something. You don't just let them sit passively. So do something. It's kind of hard in a lecture that is given in an asynchronous environment to do that. But in a classroom, if you're doing a lecture, you have question, answer, question, answer. You stop and I ask you, well, what's an example of this? So that's a way to fold that in there and make them become engaged themselves. If you're answering a question, you're engaged. So another feature, this is the second one on the list, is to improve the learning and the memory of the content in your presentation or in your learning resources or in any kind of sit down and study operation, is the organization of the content. Now that organization can be imposed from outside by the textbook or the instructor, or that organization can be built by the individual learner. Either way is helpful. If you're a novice and you're just getting through it, the organization being built by the expert for you helps that flow of information come through more readily. The reason organization helps is we generally expect that you have an organizational structure and long-term memory that is organized in some sort of hierarchical fashion. It's not necessarily like that, but things tend to clump together and they tend to fall in with each other. And you are more likely to activate a network of information that is related together if you let people know in an organized way. Okay, today we're going to be talking about, we're going to talk about dogs. You might remember that dogs are a mammal, and I start talking about this, taxonomy. Um, and that will help that student, activate the right conceptual framework for the information that's coming in. We might think about dogs in lots of different ways, but today I'm going to be talking about, the biological issues underlying what makes a dog and what makes a dog different from a cat or something like that. And so that I want to make sure I have them in the right frame of mind, not thinking about, cute puppy videos or the puppy bowl type thing. I want them thinking about the, family canine and genus Vulpes or whatever all these things may be. It's been a while since ninth grade biology. Skipping around really harms the flow of that information for your learners. They tend to get lost. They don't know where you are. Remember, I'm talking about organization right now. By the way, that's a good strategy you can do. If you feel like you've lost the thread, bring them back up and say, today we're talking about organization, which is one of those key factors that's supposed to be helpful for supporting people's memory. It's one way to keep them in an organized fashion so that they can get their content down. Now, some people like to teach in a top-down, where I give you the big idea and I work my way down to the details, versus a bottom-up, where I give you details and then we from that infer or create an understanding of the big picture. Both have their place. Sometimes it works better one way, sometimes it works better the other way, sometimes it fits my method of instruction for this particular topic. Sometimes that won't work with my particular focus of instruction. A good educator, a good expert in the discipline, generally has what we call content or pedagogical content knowledge, meaning they know the right time to use this kind of instructional strategy for that kind of material. And that comes with experience, frankly. Another key important thing, and I'm sorry, this slide's a little disorganized since it went to this format, but I don't think it'll affect your ability to follow. Location, location, location. So where the information occurs matters. And you will see in the book, Shunk's book, if you looked at that book, he talks about serial position effect. And the graphic that is there has just like a simple up and down curve that says that things that occur in the middle are the least likely to be retrieved, and things on the ends are the most likely to be retrieved. That is true, but that curve is wrong. It's just, this is a better curve because it's not a symmetric curve is the thing. The items at the very beginning of the list are more likely to be recalled than things in the middle of the list. Absolutely true. Items at the end of a list tend to be more likely recalled than things in the middle of a list as well. Also true. But things at the end of the list also tend to be recalled more easily than things at the beginning of the list in most cases, assuming all things are equal and these aren't conceptually related list items. So the location of an item in a list, and by the way, this is just pretty much talking about list learning. If you're trying to remember a list of objects, I want you to pick up these 8 things for me at the store today. Put the thing you want the most at the end of the list and put the thing you want the second most at the beginning of the list, and then work your way inward from there, because those are the things that have the highest probability of recall. As you can see with this graph, it's really, this is one of the deeper studies that was done on this back in the days. What they demonstrated was there were 3 list lengths, and they showed that this serial position effect, these primacy effects and these recency effects, were not related or were not dependent upon the number of items in the list. So if I have a 20 item list, that recency and that primacy effect both still happen. Now you'll notice that as the length of the list increases, the probability of recalling any single item goes down a little bit, right? As a list gets longer, it gets harder to remember. That's why this one is always lower than this one, and is always lower than that one. But no matter how long the list was for the subjects, people tended to recall things at the very end of a list best, and things at the very beginning of the list more likely than things in the middle. Now, there are a lot of explanations for this. The one that I like to talk about is essentially that there's something meaningful or something unique or identifying or distinct about the positions of these ends of items. There's less interaction or interference with other items because there's no next item after the last item. There's no prior item to the first item. That's one way that people explain it. Another way that people explain it is, well, in this kind of learning memory task, in this experiment, the person is given a list of items in order: ball, jump, cow, monkey, bucket, just on and on and on like that. And then I say, okay, recall, or I signal you recall. There's a problem with just saying recall. We'll get to that in the advanced class. When they go to recall, what happens is in the explanation of one model of this, the working memory model explains it this way. They kind of do a short-term memory dump with these things at the end of the list, right? And they just spit that stuff out because it's still fresh in working memory and they haven't really had a chance to rehearse it. And so those things are more likely to get out. And then these items at the beginning of the list, the reason they do better is because they're the first items and they tend to get repeated more often when someone's trying to remember this list. So they're saying the list of items over and over again. Ball, 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 jump, ball, jump, ball, whatever it might be. Okay? So that's what the primacy effect and recency effect is. Here's the thing, it's a parlor trick, in my opinion. There are a lot of studies that we talk about that really focus on parlor tricks. The parlor tricks are things that they explain or they were used to help us define how memory works, but they really don't matter much in our daily lives. How often do you need to remember the order of things in a list of 10? You don't. How often do you need to remember a list of 10 items without writing it down? Not very often. So this is one of those things that helps us understand how that working memory works, but it's not really a functional thing. One more sort of extension of this is positional uncertainty effects. This is like a next level serial position effect. And this was based on the idea that I told you first, where there's less interference. So this model shows you that this is the item position that it should be in, okay? And this is if I make an error, and so the dot is the square there, I'm sorry, is showing you how many people, when they were given a list of 5 things, were able to remember that the item 1 occurred in position 1. So this is position 1. You can ignore this bottom part about Monday, Tuesday, but they show that it works over time as well. But item 1, you're most likely to recall it in the item 1 spot. So 80% of people roughly accurately identified that item 1 occurred in position 1, as it was when it was first presented, when they came back for a recall event later. But when you looked at people who made a mistake, the most likely place they would put item number 1, so in the example I gave you, ball was the first item. Some people might say, well, the word ball, yeah, that was a word, I think it occurred second in the list, right? When they did that, if they were wrong, it was most likely they moved it only 1 slot over. And you can see it even better in this example. If the second item in the list I gave you, which was, do you remember? I think it was jump, but I'm not sure. So if you remember jump was the second item in the list, you'd get 60% of that item, 60% of people tended to remember that item in the right location. But the people who missed it, and this is the fun stuff for this, again, this is a parlor trick. This is a laboratory study by a former professor of mine, Jim Nairn, who's at Purdue. What he found was this item, number 2, you were equally likely to bump that item to the left or to the right 1 slot, but not so likely to go 2 slots away. And what that shows is that you tend to have this fixed point in your memory. You remember where things occur. You can make an error, but the error predictability is pretty strong. You can see which direction they went with these errors in the model. So people tend were, by the way, and this is a next level thing. Again, we'll get to this in the advanced class. You'll notice the difference between the square and the dot. The square is a computer model that tells us what the likely probability of their error pattern would be based on Nairn's feature model, which is what this study was testing. And the black dot is what the actual performance was. You can see it came out pretty well. And his whole model, we'll get to this at the end, is about distinctiveness and multiple cues. And one of the things he was talking about in this particular study is that position is a cue. So what order things were in, you code that as a memorial piece of information so that when you go to retrieve it later, that's one thing that you rely on in retrieval. But what matters here is position does matter, and it gets coded as a piece of information, just like the color of the text would matter or the size of the font. We catch all of that information. Position tends to be one of those things that we pay a little bit more attention to. Okay, moving on. Location, location, location. If you need a break, take a break. Now we're on to repetition. We know that if you learn something or if you encounter something once, you have a probability of remembering. If you recount it again, you have a higher probability of remembering it. So repetition is a key feature for memory. Unfortunately, people do it poorly sometimes. What they do is they repeat the same thing over and over and over again. I do a lot of research on test anxiety, and we've demonstrated in several studies and papers over the years that students with high test anxiety tend to study more than students with low test anxiety, but they tend to study more inefficiently, meaning they do the same thing repeatedly. So they'll look at the same chapter repeatedly instead of doing some deeper embellishment or elaboration process. Or they'll look at the same set of flashcards over and over and over again. And there's nothing going on when you're doing that. You're just flipping through. You already know what the next flashcard's going to be. That's great if the task is, tell me what the next flashcard is. It's not so great if the task is, do you know what the content of that flashcard is? And can you go deeper than just what is the definition on that flashcard? So some things that are related to repetition. The spacing effect. And you see this graphic I got off of Thalheimer. When you talk about the spacing effect here, this is like 100% likely accuracy, and these numbers are probably generated. These are not necessarily from a specific study. This is a meta report from multiple studies. This x-axis, as you go along on this picture, is looking at time. So let's say I have a learning event, this line right here. This is the test. And if I am going to study for the test, and I'm going to prepare for this exam, and I space out my study like this is the blue line, this is spaced learning, I'm going to have learning occur gradually over time. And then when I hit that test event, there's a possibility that I'll know a little bit less than this massed practice person, right? That's an extension, right? It could go either way. But the value is your forgetting curve is much, much shallower than in a mass learning procedure. They drop off much more quickly here. And when you look at this curve, you may remember I talked in the behavioral learning theory, they talked about the Rescorla-Wagner process. So the Rescorla-Wagner model is actually right here. And what they demonstrated with animal learning also works with human learning for the most part. That learning follows an asymptotic curve in most cases. And what that means is there's a certain amount that this person is capable of learning in this content area. And that's represented by this, unseen straight line across the top. This person with the blue line is a good example of that. Every time the person is learning here, they're learning less than they learned in the previous event. Why? Because there's less for them to learn. So what happens is you tend to learn a certain percentage of the amount to be learned that's left that is unknown to you. And as you know more and you advance along, there's less content to be learned each time, but you learn a certain percentage of that is the theory. So you can see they learn a little bit less each time, but their total knowledge keeps growing. So it's just a crossover from old old school behavioral learning with rats and pigeons and such also applies to humans. Basically, we have incremental learning processes. Well, the reason this becomes important with spaced learning versus mass learning is in a mass learning approach where it's compressed really tightly right here. Maybe I learn a lot right here. By the way, this is kind of a false jump here unless we're talking about a really long learning event, like a extended learning event. There's no reason to believe that someone on the first learning trial here is going to learn more than somebody on the first learning trial here unless they have some differential time span. Like this is a 2-hour study session, this is a 15-minute study session, something like that. But anyway, they compress their learning here, so they get these big jumps, but it's a false and illusory learning. So they can remember more about what the content was covering because there's less time in between. So you have less forgetting, if you will, less instability in the knowledge that they're holding. But then you see rapid loss of the ability to effectively retrieve that information later. You might recall in the different video I talked about a lot of students will say working memory is about a day's worth, and so this might look like that. I studied, Wednesday night and Thursday night, or just all Wednesday night for a test that was happening the next day, and then, a day later, I don't remember any of that stuff. It's in there poorly, very poorly. Whereas somebody in this case who spends time studying progressively and carefully over time, they're less likely to have major forgetting. They're not going to be as strong as they were at the end of the study session. They're going to have a little drop off perhaps, but they won't have that ridiculous drop off. This curve right here, by the way, the reactivation curve, this is where I just come back and I check in now and again. So maybe in a math class, they do this a lot where there's just practice items from previous units. They keep them there so that when you get to the final exam at the end of the semester, it's not quite such a surprise as it is if you left it all that time. The accessibility hypothesis I put here is one of the explanations for the spacing effect. What it says is if I'm looking at a set of flashcards over and over and over and over again, when I look at the next flashcard, I look at it, and if it's still fresh in my mind what's on that flashcard, I think, oh yeah, I know that, and I move on. And I don't actually process that content, or I get a validation for myself, like, yeah, I got that, yeah, I got that, yeah, I got that. And so you're not getting that deeper processing. So spacing effect, what that does is it takes you away from that context for a while. And it doesn't have to be a long period of time. It doesn't have to be days or anything like that. It can be, study something, take a break for a half hour, come back to it. Even that will work with a spacing effect. It's better if you spread it out over time, though. But when I look back at it again, my working memory's been cleared, and I can look at the content and I can actually identify whether I actually do know it. And if I don't, then I go through the process of relearning it, not as much process as the first time. It's easier the second time. I relearn it, or I make those connections again, and then that information gets laid down more effectively, and I build up, this is the other important part, I build up the successful retrieval of that information from long-term memory. So not only am I putting stuff into memory, but I'm learning how to get it out of memory. So that's one of the effective things about having that spaced out is I step away from it for a moment, and I learn it, or I retrieve it in a context, and I've taught myself how to retrieve that content. The testing effect goes along with this a little bit. What the testing effect says is actually taking a test one time and then taking another test another time, even if you don't do any studying in between, which, by the way, if you have that opportunity in my class, that's crazy to not do anything in between. But even if you don't do anything in between, if you take the first test and you have a little break and you come back and you take the test again, the probability of you scoring higher on the second test is very high because that testing effect was another learning event for you. You had another memorial experience, you had a retrieval event for all this content, and you increase the probability that you have some sort of consolidation with your memory. Now take that testing effect and apply it to a personal situation. Very few classes allow you to take a test twice, unless you're doing a pre-test, post-test, or something like that. You can test yourself, and self-testing is one of the most powerful and effective strategies that people can use to prepare for tests that they're going to take later on. You ask yourself questions, don't cheat on it, like give yourself a real set of questions that come from the chapter or the book, or a peer gives you a set of items. It forces you to try to retrieve information in a contextually relevant and realistic setting. Very, very strong process. And then finally, one last thing is meaningful repetition is far better than simple rote. So if you're doing a repetitive experience, that's fine, but try to use more meaningful examples for your repetition than just straight definitions. Unless, if the only thing you have to know is the definition, work that definition over and over again. If you're an actor and you have to know your lines, rote repetition, because you need to know everything about the line, exactly how the line goes. You don't need to know, like, what is the underlying philosophical framework for the speech in this play? No, you need to be able to deliver those lines. Now, understanding the underlying philosophical framework may make your lines more believable. I'm not an actor. Something else that came up in the chapter that will promote your learning. Remember, all these things are about ways that we can increase the probability that you'll retrieve information later, or have a deeper understanding or better representation of content later. But one way you can promote your learning is to engage in what they call deep processing, or use the levels of processing at the greater depth. There are lots of different ways that people say this. What they mean by this, this came out in the early 1970s and was carried out for a while throughout the 70s in particular. They said that all this research done on lists misses the point that most of the stuff we want people to learn, we want them to understand it. We don't want them just to be able to retrieve it and spit back out a list of 8 items. So the depth of processing models came around to focus on, there are different ways that we can try to store information in long-term memory. The deeper you go with that attempt to memorize or understand or capture the information, the deeper you go with that, what you're really doing is you're engaging in more semantic focused or conceptually driven or understanding level thinking. And those deeper levels of thinking are more likely to put things into long-term memory in an organized structure that will make it available to you later. This graphic is one of the examples of the work that the Kraken, Lockhart, and Tulving and Thompson. These are kind of the big names in this field back in those days. These were the things they were focusing on. They were focusing on perceptual awareness in your learning task versus semantic awareness. So they would give people a list of words and say, okay, I want you to circle all the E's while you're going through here. So I know they were reading the words because they had to, pay attention to the letters of the words, but they didn't necessarily really master the list, as opposed to me telling them, okay, now when you go through that list, I want you to, tell me whether or not the word rhymes with, or give me a rhyming word for that. It would be better to say, tell me whether or not it rhymes with, they have an example. Does the word rhyme with tool? And I give you a list of words, right? And you just had to compare it. And so that got into a phonological determination, which is a little deeper than a textual interpretation was the understanding, because I actually had to say the word instead of just look at the word. And then the last one is making a determination about the utility of the object, or an evaluative judgment about the word, something that made me think more about what is the meaning of the word. And when you do that, the idea is that this farther end is deeper processing, and you're more likely to retrieve that information later. But of course, there's a trick, or there's a hitch. The encoding specificity principle, which is mentioned in a couple of different places throughout these chapters, demonstrates that what we call material appropriate processing is a real important feature. Or another term for this is transfer appropriate processing. There are two lines of thinking that come back to the same principle. What it says is the method of study, or the method of encoding, that is available to me at the time of when I'm presented with these materials, the better that matches up with or supports the long-term outcome goal of the memorial task I'm going to be given, the more likely that encoding event will be successful. So if I need you to be able to tell me how many E's on average were in every letter or were in every word that I gave you, then this visual analysis would be more effective than tell me what, was the word. Is this word something that you would store in a bread box, or is this something that's, would it appear in a toolbox? And that was the kind of question they would ask you. If I want you to remember rhyming words, then a rhyming focused encoding activity will be more likely to be successful than something that's semantic. So depth does not always win, is the key point. When you want to go for understanding, long-term retention, uh, key points, then depth works. But not every memory task is focused on those key issues. Sometimes we just want people to spell. Elaboration. So elaboration in the basic information processing model, we talked about elaborative rehearsal. That's this. Other people refer to the term embellishments. That's this. Some people will call it just making learning meaningful, make the content personally relevant. That's this. The idea here is that you give the learner an opportunity to expand beyond what is given to them. So if I just read it and I'm just receiving the content, then that's one thing. But if I do something with the content, maybe I write down a summary statement. That's really, really strong, by the way. If you just write down a summarization of what you just read, that works really well, far better than rereading the same passage, assuming you understood it when you read it. So that writing down a summary is an elaboration. If I give an example, that's an elaboration. And what's going on there is it's requiring you to have deeper cognitive engagement with the content than merely receiving it. And we'll talk about generate versus read here in a minute. It promotes deep processing is the general idea. And it provides multiple cues, going back to that Nairn model that I'll mention in a minute about multiple and distinct cues. And so this is just an example graphic that a teacher of writing uses to help students think about how can I elaborate in my own writing. That's how your memory works too. More elaboration in your memorial process. When you give yourself more elaboration to work with, you have a higher probability of storing information that's useful to you and can be retrieved later because more cues, more connections, more meat, if you will, to work with, the more likely the student will be able to generate the content. Okay, we're on elaboration. Getting to generation. We have two more general principles and then cognitive load theory. So if you need a break, take your break. Remember, one of the key points we'll get to in cognitive load is break up your content. Don't take it all at once. Slow it down. Make sure you understand it. And that's called the segmenting principle. So my breaking things up into multiple slides follows the segmenting principle, but me shoving it all at you in a 35, how many minutes, 40-minute video so far, that's not a good segmenting. So you're going to have to self-manage this. So the generation effect is one of my favorite effects, demonstrates that when learners read content, they can learn it, of course, but they're more likely to remember stuff when they are involved in the creation of their understanding of that. And so a lot of times what they would do is they give the students a task where in one case you would just read the content. In another case you had to fill in blanks and create something yourself. And they made sense what the fill-in was, but they were actively engaged in the construction of that passage that they were doing. You might think about there was an old magazine, I assume it's still around, called Highlights, and you would read along and it had some words and then other places they had rebuses or the little pictures that went in there. And the children working through that would be reading some words and then they would have to translate what is this picture supposed to mean and then fill that in. That's more of a generation effect than merely reading, or even worse, or even lower level is just listening. The idea is if the kid is going through and they can't read all those words, yeah, but they know what that's a dog, right? So if I'm reading along and say, well, and there's a picture, and the kid might say ball, was chased by the dog, then the child is more engaged in that and he or she is generating the content. So what this pattern of results has demonstrated is that when you are actively engaged in generating the content that you're supposed to remember, you have a higher probability of remembering it than when you just read or quote unquote receive the information that was given to you, that was put out there for you. This is a critical feature, and we'll talk a lot about this when we talk about the constructivist learning principles in a week or two. But it's got some cool effects that go with it. So here's a great study put out by Merlin Wittrock, who's one of the coolest names in educational psychology. Back in I think this was like in 76 that he did this study. So this is a really old study, and then it just kind of went away for a while. And then constructivism came back in the 90s and thereafter, and people got excited about it again. But his generative processing model focused on the idea that the more you engage students in being generative learners, where they create content, which we now just think of as constructivism, led to these major outcome differences. So real quickly, to break down this figure, and this is something that I expect students to get better and better at over time. This, and you would have the whole article normally to read, so you'd be able to suss this out, but I've read this a few times myself. So there were 3 organizational patterns for materials that students were given. Lists of words. Unrelated, so they're just a random set of words, they're not connected. A random organization of items that were related to one another, but they weren't listed in that organizational flow. Does that make sense? So like I might have a list of related items, but they were scrambled. And then in this case, they were related items, but they were clumped by the relationships within them. So maybe, 3 kinds of weapons and 3 kinds of rooms and 3 kinds of names, for Clue or whatever, the board game. So in this case, when they were given the order, the hierarchical organizational order of items in the way that it made sense, performance for people who just did repetition was higher than in the other 2 conditions. But the beautiful part is when they were engaged in a generative process where they had to create information in this process, I forget the exact process but I think they had to put them in an organizational flow or identify the hierarchical categories, something to that effect. They outperformed. And you'll see in the generative processing always outperformed the non-generative. Now, the beautiful thing that you see here is if there is a hierarchical organization at all, and the students are induced to put them in those hierarchical categories in their memory and retrieval process, whereas these people were not, you see this huge spike that if it's organized, if you're giving people organized information and you don't give it to them in that organized fashion necessarily, but you give them time to put it in that organizational fashion, they perform just as well as when I give it to you in an organized format. Remember, this is lists. It's not a big long lecture. This is a list of items. The person had the opportunity to put these lists in the right order. When I am in control of my learning and the learning is something that I can put into a format that makes sense, and I'm actively processing the information generating, then performance is maximized. That's the takeaway from this. Also, one more thing here is personal cues are greater than provided cues. So if you tell me, well, here are some things to help you remember this information, that's good. But if I generate those myself, I tend to be more effective in using them in the retrieval event because, I know my own head. One more thing that helps with learning is context. So if you can learn in a lab, if you can learn in the field and get practice with materials, really out in, if you want to study environmental science, go out in the environment, if it's available to you. You can't always go to all the environments. But the value of these contextual settings is you get all the different variations and variables that are meaningful and matter. So when I'm out there collecting water samples in a certain stream, let's say, on a cold day, maybe I pick up new information than when it's a hot day. Maybe I start to bring all that stuff together and make a better understanding than if you just tell me that it might matter. Same thing in a lab. If you're in a lab setting, you're doing all those things that you do in a lab, that context helps you encode all the relevant important cues that are tied to the learning activity that you're engaged in. Doing it in a virtual lab, that's, that can work, but not as well as being in the real lab because there's more cues there for you to encode. Now, some people like to take this overboard and they say, well, then if you chew gum when you're studying for a test, you should chew gum when you're taking the test. That'll make you more likely to study. Or I heard once that if you use this pencil to write your notes, you should use that pencil with your final test. There's no good evidence to support that stuff. There's a couple of funky studies out there that have shown that uh, uh, being under the influence of various substances, if you match that up from study to testing situations, that helps. But most of those are uh, kind of ridiculous studies. My favorite one is the one with alcohol. Alcohol actually did work out pretty well. And what they showed was if, let me make sure I say this right. Um, Basically, the finding from the alcohol studies, it's an encoding specificity thing where it says if you're under the influence of alcohol at study, later on when you're taking the test, do you do better if you're under the influence of alcohol or if you're not? And the idea is that the alcohol is going to change your storage mechanisms, and so those contextual cues be more helpful when you're studying when you're in the test because they'll match up. Really, what the study showed was if you're going to drink, it's better to drink when you're taking the test than when you're studying for the test. Because at least when you're studying for the test, if you're not loaded, you have a better chance that information will be organized in a meaningful fashion. So that if you are loaded when you're taking the test, you have a better chance of getting it out because it was stored well in the first place. But getting loaded during the study time and during the test isn't any better. And by the way, being drunk while you take the test hurts your chances on performing on the test. So don't drink before you take a test. Um, they've done similar things with caffeine. They've done similar things with all kinds of things. The one study that actually demonstrated a meaningful effect with these contextual cues was a study where scuba divers studied words underwater versus out of water and then flipped the situation for the testing. And they found that when you studied a list of words when you were underwater in scuba gear, that you tended to perform better when the test occurred underwater as well. Um, that's I mean, that's contextual relevance, but that's about the only study that's ever proven that to work consistently. And no one really knows why it worked in that particular situation. And I don't think many of you are going to be doing scuba diving uh, memory experiments, so I don't spend a lot of time talking about it. Finally, multiple and distinct cues. Kind of the big general overarching thing with all the cognitive models that I'd like you to think about. When you're learning, you're taking in cues from the environment. And you're putting all those cues together in some sort of organized fashion and putting them into your memorial system, your long-term memory, whatever it may be, however you want to think about it. The more cues you have, the more likely you'll retrieve that information later on. On top of that, the more distinct cues you have for a piece of information, the more likely that when I give you that cue, you're going to come up with that piece of information right away because it's specific. It drives you right to the main point. So multiple and distinct cues are the things that drive good memory retrieval in a learning event. The other thing that ties to this that I wanted to point out real quickly is the dual coding effect. This provides for both multiple cues and many times distinct cues. So dual coding says that you can bring in information in a visual context as well as an auditory context. And if you do that in a synced fashion, that you have a higher probability of making a meaningful memorial representation of the content. That's why we put labels on uh, objects in elementary school classrooms, particularly for students who are either A, learning to identify letter print identification or recognize that this is a sight word called chair, or if you're a second language learner, you're in the room, you know what a chair is, but you don't call it a chair in your home, you call it something else, whatever your home language may be. And you see this word, it will help you, is the presumption, start to make the transition to recognize the English representation for that word. Another example of a dual coding learning resource is this wash your hands from the CDC, which everybody should wash your hands. But it shows you the steps, right? It's got visual as well as textual information. Now, true multimedia coding would maybe have someone narrating this, but this is when, like, you think about the getting on an airline, and the flight attendants will tell you, okay, well, everybody take out the thing, and I'm going to show you the thing, and we'll do all of this, and nobody takes out the thing and looks at the thing. But the ideal would be I would take out the thing and see what my safety precautions are as the individual at the front of the plane or in the middle of the plane, wherever it may be, is walking me through those important steps. Key here is that you want to assault the content with good cues and lots of cues, and that increases the probability that you'll be able to retrieve it when you need it. Okay, all this comes around to major things that can help you remember or learn things, and then retrieve them when you need it. One more topic that shows up in this book that I like to come back around and just wrap this up is cognitive load theory. So first of all, cognitive load theory is not a theory of learning. It's an explanation of the limits to learning that we all have. So we can't do it all at once. So cognitive load theory says you have so much working memory capacity. You can handle only so much. And when you fill up that working memory capacity with these different kinds of load, pretty soon you're full and you can't be efficient, you can't move on, and stuff's going to get missed. So this is very popular with content and curriculum designers, web page designers who are trying to get information across to people, instructors, etc. And it's a simple way to look at a learning situation, try to figure out why isn't somebody learning this content, or what can I do to make the learning of this situation easier? So the triarchic theory of cognitive load says there are 3 kinds of cognitive load. There are other models of cognitive load that only look at 2 kinds, but we're going to talk about the triarchic model because it's more pro or positive psychology in nature, because it focuses on what you can do to spur greater learning, not just minimize problems. So the first kind of load, this is the load that is it's a drag on your learning potential. Extraneous cognitive load. This is distraction. This is poor organization. This is too much text on a slide, things like that. Anything that takes away from your ability to essentially process the content. This is called extraneous. This activates in your cognitive system what Rich Mayer from you'll see him in the book. He's UC Santa Barbara, big influential. The cognitive theory of multimedia learning that I presented in the other video, that's him. He refers to anything that you have to do that fills up this extraneous cognitive load as extraneous processing. We don't want to do that. The goal is to eliminate as much of this as possible. There's always going to be distraction. There's always going to be something that takes away from an optimal learning situation. But what an instructor can do, a good instructor, is to reduce the amount of this extraneous cognitive load or extraneous processing a learner is going through. The second kind of load is called the intrinsic cognitive load. This is what, and this varies from person to person. The particular content that you need to get through on this particular learning activity imposes upon you a certain amount of memorial load or working memory load or cognitive load that's called intrinsic cognitive load. And that's what's called the essential processing. The reason it varies from person to person is, when I look at this stuff, I've been teaching this for a long time. Something new comes up, I can add that in very easily. It doesn't fill up a lot of my working memory capacity because I already have all this other background knowledge. When you're looking at something that you're an expert on, you can zip through it much more quickly than somebody else might be able to because they don't have that basic background knowledge. So this intrinsic cognitive load varies from person to person, and it's necessary though. So you can't get rid of it. But what you can do, and we'll talk about this in a moment, is help them manage it. So when I was repeatedly referring to take a break, segment, don't do it all at once, manage the flow. That's called the segmenting principle. That's one way that you can help manage that essential processing and manage the intrinsic cognitive load. You can't lower it, but you can regulate it so that you're not getting overblown at any one time. Another way you can help manage intrinsic cognitive load is to do what we call pre-training or preloading. Give information up front before you go into an essential learning activity so that they don't have to manage a whole bunch of new background information. So you come in with a better base knowledge, and then you're not so overwhelmed. Finally, the germane cognitive load. This is the goal. This is what you're shooting for, what we call generative processing. This is when you have enough working memory capacity left over after you've accounted for the extraneous processing, where you're getting distracted or there's extra junk you don't want, seductive details, all those garbage things that you really don't want to pay attention to, worries, feelings, doubts, etc. The essential processing required by the intrinsic cognitive load is managed, and you still have working memory capacity left. And I engage you in really making deep connections. And that's when the generative processing occurs, where you're making new gains in your understanding about content. So you're not just getting through it. You're making major or even minor cognitive gains in this particular domain of understanding that you're dealing with. So the implications of cognitive load theory for instructional designers. First, you reduce the individual's extraneous load, as this graphic has, reduce the noise. The second thing is you want to manage that intrinsic cognitive load. You want to slow the pace down, not to make it slow, but to make it manageable. You want to make it so it's a nice and steady flow of information coming through so that the individual doesn't get blown over by too much content at one time. This can be by, pacing information, or it can be by preloading, or it can be by taking breaks and doing comprehension monitoring as you go. And the last thing, of course, is to foster generative processing. Give meaningful learning activities that allow them to apply the content in a personal and effective way. I'm looking at my graphic. I'm coming up on exactly 60 minutes, which that's a long presentation. I hope you broke it up for yourselves. You can always watch it again. That repetition factor, I'm sure that's not everybody's first choice right now. Have a good day. Hope everybody's safe.